All right, AP Physics. This is the answers video for the week 12 assignment. I'd like you to turn that in. It says due Saturday. I'd like to make that Monday. And that would be the 13th. But that's a due date. It will be considered late after Monday the 13th, okay? So use this answers video to get through it. Okay, let's get going on this. All right. First question is kind of involved. It might be the hardest question on the entire assignment. So just brace yourself and understand that not all the questions are this challenging. So if you look at it, looks like a classic conservation of momentum problem. So two blocks, masses m, m2 are shown above, initially travel at the same speed v, but in opposite directions. They collide and stick together. How much mechanical energy is lost to other forms? So the strategy for this is we need to know velocities after to get mechanical energy, to compute the mechanical energy after. So first we're going to do a conservation of momentum problem, and then we're going to do a conservation of energy problem. Now we haven't done the energy unit, so this is really a learning problem. If you don't know how to do this on your own, that's okay, but now you're going to learn how to do it, and I'd like you to practice this one because this is one of the more challenging problems. So for kinetic energy, it says mechanical, but there's no potential energy involved. So for mechanical energy, that is the kinetic energy, is 1/2 mv squared. That's the general formula we'll need. For conservation of momentum, it's m1 v1, mass times the velocity of the first block, plus m2 v2, and that's before they collide. That's got to equal m1 v1 plus m2 v2 after they collide. So let's figure out, in order to know the velocity after, we have to do this conservation of momentum problem, and we need to know the velocity after they collide in order to compute kinetic energy after the collision. Okay, so let's go ahead and set this up. So we have m times v is the momentum to the right, so it's going to be, and we'll use capital M because that's the block is capital M, plus, but we see that it's moving to the left, so we're going to say minus. Well, let's put a plus negative, in other words. So it's plus 2m times negative v. Okay, all right, and that's going to be the momentum of the two blocks together. So when you add those together, you get mv minus, I'm going to bring the minus sign out, minus 2mv. Okay. And if you do the math on that, 1 minus 2 is -1, so it's minus mv is the total momentum before the collision of the two blocks. Now you come over here and do conservation of momentum. So after, let's read this carefully. Two blocks of masses m1 and m2, so you want to underline those. Initially travel at the same speed v, that's key. The v is the same in both cases, but in opposite directions. They stick together, that's a key. The inelastic collision. So it's not going to be conservation of energy. How much mechanical energy is lost to other forms of energy? In other words, just lost, okay? Because energy is neither created nor destroyed, so it has to be lost to other forms of energy. Okay, so what is the mass after the collision? They stick together, so m plus 2m stick together, and that's going to be, I'm just going to write it like that, m plus 2m. That means it's really 3m, in other words, okay? And what we have to get here is we have to end up with the same momentum, minus mv, the same as over here before. So this again equals 3m. So just ask yourself, what velocity would they have to be going at? So the 3m times some velocity gives you negative mv. Again, you have to have your basic math skills for fractions, okay? The answer would be negative 1/3 v. If that was a tricky calculation, come and see me, because you need to know your 7th grade fractions, 8th grade fraction math, okay? You can't do college physics without that. So we now know the velocity after, And now we can go ahead and compute kinetic energies. Okay, so let's start with the kinetic energy of the system before they collide. So it's this formula right here. It's 1/2 mv squared. Okay, and then you add it to this one, just like conservation of momentum. Except the difference is it's going to be 1/2 times 2m. And before the collision, the velocity is negative v. So it's negative v in the parenthesis squared outside. Okay. All right, so let's add that up. You get 1/2 mv squared plus 1/2 times 2 is 1. And m negative v squared is v. It's positive v. So it's m times positive v. And you multiply that by 1/2 times 2 is 1, and you get mv. So be sure you understand that math, okay? Now we're going to add those together to get the total momentum of the two blocks, total energy of the two blocks before the collision. And it's 1/2 plus 1. There's an implied 1 there. So that equals, don't write 1/2. Write 3/2. Always write as an improper fraction. You can't do math on a mixed fraction, 1/2. You have to have it as an improper fraction to do further math. So it's mv, and I should have put squared here, and that's squared. So that's the total energy before the collision. Now we need to figure out the total energy after the collision. So let me write that KE before. Not worried about this. This problem doesn't take that much space down here. That's the total kinetic energy before. Now I'm going to come over here and do the kinetic energy after. The kinetic energy of both blocks before the collision. Now we need the kinetic energy after the collision. And remember, we're treating it like a single 3m block, a mass of 3m. So the KE equals, in general formula, 1/2 mv squared. So that's going to be 1/2, and the mass is 3m of that new block. Okay, and the velocity is negative 1/3. That's what we figured out with the conservation of momentum part, v squared. And the square goes outside the parentheses. This is the velocity, and then you have to square it. Okay, so let's just do this one step at a time. Equals 1/2 3m and 1/3 squared. You square the top. That one squared is negative 1 squared is 1, and you square the bottom. 3 squared is 9. So it's going to be 1/9 v squared. And you don't need the parenthesis anymore. I started to write it, but you don't need it anymore because you've distributed that to this and to this. So let me just rewrite that. Okay, so now the m and the v on both sides are going to cancel out. You got mv squared on the right side, and over here you have mv squared on the left side. So forget about those. Let's just deal with the numbers. So it's, and I don't know why I wrote 1/2 here. So let's be sure you're clear on what that number is. It's 1/3 squared is 1/9. Okay, so it's 1 times 3 times 1 is 3. And on the bottom, it's 2 times 9 is 18. And we can reduce that down to 1/6. So again, forget about the v squared and m because they cancel out on both sides. So what we did was we went from an energy of 3/2 mv squared to 1/6 mv squared. So what is the difference between these two? That's what the question's asking for. You started here, you ended here, so we need to do a subtraction to find out the difference. So the change in kinetic energy equals 3/2 minus 1/6, what you ended with, what you began with minus what you ended with. Okay, now you got to know how to do fractions, okay? If you don't, come to me and let's practice these. I use the crossing arrows method. So you put a 2 on top here, a 2 on bottom here. Okay, and this 6 comes over here. Use a 6 on top there, a 6 on bottom there. Okay, so 6 times 3 is 18. 6 times 2 is 12. Minus 2 times 1 is 2. And 6 times 2 is 12. So you have a common denominator. 18 minus 2 is 16 over 12. And that reduces down to 4 over 3 mv squared. Okay, we just kept that off. So the final answer officially is change in KE equals 4 over 3 mv squared. And that's this answer right here. All right, you have to show the work on your homework assignment. That was maybe the most complicated, or one of the most complicated on the assignment. Okay, I didn't leave myself much space for the next problem, so I'm going to draw a box like this. All right, so the question is, student obtains data on the magnitude, that means the number, the amount of force applied to an object as a function of time, and displays the data on the graph above. So the rule is very simply that momentum equals impulse J, which equals the area. Write this down. I want you to make these notes, because when you review this 6 months from now, it may not be obvious. Under an F dash T graph. It's the area under the graph. Okay? So what is that area? Let's just sketch out what we have here. It goes up in a straight line from there, and that goes from 5 to 25, and then it goes from 0 to 4 seconds right there. So the area under this line is everything in the triangle plus everything down here below the triangle. All right, so what's the formula for a triangle? So it's 1/2, so triangle, that's delta means a triangle, is 1/2. I shouldn't use that because it'll confuse that with change in. I'll just call it a tri. Okay, is 1/2 base times height. So 1/2 the base, so the base goes from 0 to 4, that's 4. And let me write the 1/2 first. 1/2 4 times height from 5 to 25 is 20. So 4 times 20 is 80, and half of that equals 40. So this area in here is 40. Okay, right there. Now you need this area down here, and that's going to be down here is going to be, it goes 0 to 5. It's a rectangle. So it's 0 to 5. So I'll just write rectangle. Okay, and that's going to be base, or excuse me, length times height. So it's 5 times 1, 2, 3, 4 is 20. So you add these two together. 40, I'll write the 20 right there. 40 plus 20 equals 60. And it's in the units of momentum or impulse, which is kilogram meters per second or Newton seconds. That's your final answer, and the option is down here right there. Okay, all right, next question. Okay, it says object X, which is the dark dots, is traveling on a horizontal surface and collides with object Y. The velocity is a function of time for the object X and Y below. During and after the collision is shown on the graph. Both objects have a mass of 2 kilograms. It's nice, they actually give you a number. Which of the following correctly describes the momentum P of the system and the kinetic energy? And now it's simply asking you for this, all right? So a choice. You don't have to actually give a number. Okay, so how do we answer this? First of all, you write the following. P, momentum. And they like to put a little vector arrow above, so I'll do it. It is a vector. Is always conserved. Boom. Simple as that. That means these two answers, C and D, which says P is not conserved, you can get rid of those. Okay? So we need to know whether kinetic energy is conserved, all right? Okay, so you have to do the same calculation we did in the earlier problem. The kinetic energy of object X, it has a velocity of 4 and a mass of 2 is given in the problem. So KE for the system, I'll write this out this time, equals KE of object X plus KE of object Y. And I want you writing these formulas like this. Don't shortcut this. Okay, write out the general formula. So what's KE of X? So I'll go over here and do that. It's 1/2. The mass is 2. And the velocity you see right here is 4. Before they collide, it's 4. So it's 4 squared. So it's nice they give you actual numbers to work with. Now you add that to the kinetic energy here, and it's 1/2. The mass is also 2, and the velocity is -2. And you square that. So 4 squared is 16, times 2 divided by 2 is going to give you 16 for this one. Over here, -2 squared is 4, times 2 is 8, half of 8 is back to 4 again. So that means the total KE total equals 20 joules. Okay, so now we need to see what the kinetic energy is after they collide. And it was pointed out in class that they stick together, then it couldn't be a conservation of energy, because sticking together is an inelastic collision, and inelastic collisions are not do not conserve energy. But let's do the numbers anyway. So they both now have a velocity of 1. So we're going to add that together. So this is the after. This is before up here. And after. And the first object is 1/2 times 2 times 1 squared. And the second object is the same thing, because they're now going the same velocity right there at 1. So it's 1/2 2 times 1 squared. So this equals 1. 1 squared is 1. 2 times 1/2 is 1. So that's 1 plus this same thing. 1 equals 2 joules. Okay, so 20 joules does not equal 2 joules, which you have the energy you have after. So KE is not conserved. Okay, there you go. That takes care of that. Okay, I'm going to skip 4. It, to me, doesn't make sense. If I tried to diagram this, I can't do it. So I'm just going to tell you the answer is B, but ignore it. Okay, you don't have to do it. Okay, you don't have to do this one. All right, next. All right, here we go. 2 objects, same mass. Okay, so let's actually call that M and M. Okay, 2 objects, same mass, travel in the same direction along a horizontal surface. Object X has a speed of 5 meters per second. Object Y has a speed of 2 meters per second, as shown in the figure. After the period of time X collides with Y, you can see that's happening because this is going faster than this, so eventually it's going to catch up with it. So consider the situation in which the objects collide but do not stick together. Now that doesn't mean it's a perfectly elastic collision, so you can't assume conservation of energy. Which of the following predictions is true about the center of mass of the 2 object system immediately after the collision? Okay, so let's set this up the way we did in class. I'm going to make this M, and this is 5 meters per second. Both are positive. So it's going to be 5m plus 2m equals 7m is the total momentum of those two together. That means after the collision, it's still going to be 7m. All right, so again, you're going to have m and m. All right, and that's simply going to be some velocity of this. So that means that the velocity of this one, the velocity can change, but the velocity 1, we'll call it v1 and v2, has to still equal 7m. So therefore v1 plus v2 still has to equal 7. The m's didn't change, right? So you had 7 here, so whatever this is, they could be different. This one could have slowed down to 4, and this one could have sped up to 3, but whatever they add up to, they have to still equal 7, conservation of momentum. Therefore, the velocity of the center of mass does not change. Okay, think of the center of mass meaning the two of them together. Think of it as taking the two of them and making them into one object. Okay, so the velocity of the center of mass does not change, okay, on that one. All right, next. Since the position of two identical carts on a straight horizontal track is a function of time, which of the following statements about the magnitude of the momentum of the two-cart system center of mass is true? Okay, so the masses are the same. So when we analyze this, we've got the two-cart system. Just think of it, what they're asking is the total momentum of the two carts together. And they're labeled cart 1 and cart 2. So momentum of 1 times velocity of 1 plus momentum of, or mass of 2, excuse me, I said mass of 1 times velocity of 2. Okay, the masses are all the same. So we can ignore that, because it's just going to cancel out throughout the entire problem. All the masses are the same. So let's just deal with velocity. V1 plus V2 is the two-cart system before 2 seconds. And over here is after 2 seconds. Okay? So that's going to be it's going to be, again, we're just going to be dealing with V1 plus V2. So let's look at the V1 and V2 before. So what is velocity? It's the slope of a position time graph. It's this, okay? So you need to have that fact just memorized, however you do that. Delta X, or D on this axis, we'll call it delta X, position, and time over here. All right, so the slope of that graph is going to give you the velocity, how fast it's going. So before 2 seconds, what's the slope of each of the carts? Well, they move up 1 meter for every 2 seconds, okay? So that's 1 meter over 2 seconds, and that's the velocity of cart 1 equals 0.5 meters per second. And for cart 2, V2, it also moves, well, this is cart 2, this is cart 1. It doesn't matter, they're the same. Okay, cart 1 moves up 1 meter and over 2 seconds, so it's 1 meter over 2 seconds, and that equals 0.5 meters per second. So if you add those two together, that's the velocity of the center of mass of the two carts. Center of mass just means you're treating the two carts like one object, okay? And so where is the middle of the mass of those two objects? And if you add those two together, you get 1 meter per second. That's before 2 seconds. Before 2 seconds right there, okay? All right, now after 2 seconds, so we're going from here on, cart 1 stays at ½ meter per second. It goes, well, it goes from 2 to 4, not quite, let's see. it goes from 2 to 4. So V2 or V1, let me do that right, is it goes from 2 to 4, so that's 2 meters, and it takes it 1, 2, 3 seconds. So 3 seconds. So in decimal form, you could say it's 2/3 or it's 0.67 meters per second. And V2 is here. It flatlined. It's 0. So it's 0 meters per second. And when you add those two, you get 0.67 meters per second for the velocity versus 1 meter per second. So the answer is the P center of mass. Again, we don't have to think about mass because all the masses are the same, so we can just eliminate them in talking about them, just deal with the velocities. The P center of mass is smaller after 2 seconds than before 2 seconds. That's the correct answer. All right, that's it. Let's go. All right. During an experiment, a student records the net horizontal force exerted on an object moving in a straight line across a horizontal frictionless track. The graph above shows the force as a function of time, so it's a force time, okay? So write this down. Momentum. This is required on these problems, to write down these general principles, okay? You say, but I already know that, or how do I know whether I need to write it or not? Write it, okay? I want the general principle. It's the area under a force time graph. This is a force time graph, okay? So what is the area under this graph? Now, let's continue reading though. Of the following, which is the best approximation of the magnitude, the amount of change in momentum of the object between 0 and 4 seconds? And I should actually have added that. It's delta P. Okay, so be sure you know what delta means. It means change in momentum is the area under it. So from 0 to 4, it's this area right here. So I'm going to draw a line like right here. I'm going to create a triangle. So this is the area under the triangle here. And what is it? It goes from 0 to 10, and it goes from 0 to 4 here. So 10 times, so it's going to be 1/2, 10, that's 0 to 10 there, times 0 to 4 there. So 10 times 4 is 40, half of that is 20. And that's kilogram meters per second. All right, so this area is 20. I'll just write a big 20 there. Okay, now, look at the answers. They give you 20, 30, 40. Magnitude of momentum cannot be determined. Yes, it can. We just said this is the rule. But it takes up more than just this triangle. It takes up this area up here. So how much more does that add? Well, it doesn't double 20. If this is 20, this area right here is not 20. It's something less than that. So the answer can't be exactly 20 because it's more than that. It didn't double 20. That's not 20 there. That's what it would have to be to make this 40. It's just a bit more than 20. So they're just saying that you can kind of make some estimates in your head. So the answer to that one is B. All right, next one. The graph above shows the position X as a function of time for the center of mass of a system of particles. Okay, again, if you've got a system of particles, just think of them as one big massive particle, one giant block of mass, okay? That's what they mean. Of a total mass of 6 kilograms. For a very short time interval, around 2 seconds, an external force is exerted on an object in the system. What is the resultant change in the momentum of the system? Okay, it is a position time graph, so that means the slope is the velocity. So write this down. Okay, and what's the question asking for? Change in momentum. So what is momentum? It's mv. So we're given a mass. They said 6 kilograms, and we can figure out the velocity by the slope of these lines, okay? So from 0 to 2 seconds, the momentum is going to equal the slope of this line. So what does that line do? It goes from 8 to 12 on the vertical axis, and it goes from 0 to 2 on the horizontal axis. So it's 12 minus 8 over 2 minus 0 from here to here equals 4 over 2, which equals 2 meters per second is the velocity. Okay, and I should have, let me scratch it. That should be velocity equals the slope. That's the slope. I just did the, from 8th grade math, I did the slope of this line right here. So P from 0 to 2 seconds is going to be the mass of 6 kilograms, 2 meters per second equals 12 kilogram meters per second. So that's from 0 to 2. Now from 2 to 5, we do the same thing. So the velocity is going to be, it looks like it's 9 minus 12. And it's 5 minus 2 on the horizontal axis. So that's going to be negative 3 over positive 3. That's going to equal negative 1 meters per second. So the momentum equals 6 kilograms times negative 1 meters per second, which equals negative 6 kilogram meters per second. Okay, so there's your velocity after 2 seconds, excuse me, momentum after 2 seconds. There's momentum before 2 seconds. So it wants to know the change in velocity. So it went from positive 12 to negative 6. So it's positive 12 minus negative 6. You take the final momentum and you subtract the initial momentum. We said that before. So I'm going to come up here. Change in momentum, delta P, change in momentum equals momentum final minus momentum initial, 0. Okay, so final is negative 6 minus, let's write it here, negative 6 minus the initial is 12, and that gives you negative 18 kilogram meters per second. Okay, and that's this answer right here. Okay, so look at that, get that down, copy it a second, third time until it really makes sense to you. Okay. All right, so I'm going to wrap up this video right now, and I'm going to do the rest of the problems. I'll do them on Friday. They will be up by Saturday. This is due on Monday. After Monday, it's considered late. So get it done over the weekend, and I will take care of that.